if we can go to the QEpy example, I prepared some Jupyter Notebook just in case some people want to use Jupyter Notebook. For example, we look at the SF.
So Sashwara and anybody who does prototyping, right? Then this could be really useful, I think, if you do prototyping.
And I just copied the code from the slides, and you will see that this is very simple SF code. First step, we import driver, build the communicator, and build the driver, run SF, check converge, all the steps, and we can run it here. Hope it works. Okay, now it's running SF. Maybe you're curious why I didn't see the output, because normally when we run the QEs, there are a bunch of output in the screen. So we want to avoid that, especially when we run on the Jupyter Notebook. So we have this log file. If you give a file name, all the output will go to there. But if you also can give a flag we call true. What this true means that when you write, you can get output simultaneously. That you can every step we want to see what's the output before last time I get output, and you can directly call get output. Later I will show you what that means. But here we will put everything to this file, and you can check what's on the file. And we get SF converge, we check convergency, it's true. What's the error is SF error we got. How many steps? 27. And we want to calculate NG. Okay, this is the NG we calculate. And we also can get false, we will run false, get stress, that's it. Because it's still on the file, so we have a function called get output, because all the file, and if you run this, it will read all the output, and I only print the last 20 lines. This is output, which is the same as when you run the p.sf.
And is the convergence defined by the density or by orbitals? Or?
Okay, yeah, this convergency is we defined on the input file, which is
no, she meant the algorithm.
The algorithm
like
is
criterion, I guess.
Yeah.
The output density and the difference of output density and input density, and we take that difference, calculate the heart rate energy. So that's energy we got for this. If they are the same, just put it 0. Heart rate energy of the density difference.
Are you free to change that though? Like if let's say if we want to get accuracy of orbitals, for example.
Yes.
You could do it. You write it right in there.
Yeah. Okay. Yeah. That's what I'm gonna show the next iterative way. When we do that, we have this convert. So instead of make this one convert, you can write your own converter. Yeah.
Okay.
Right.
What are the default units?
Default unit is Rydberg.
And Rydberg and Antron?
No, just Andy. Actually, it's Rydberg.
No.
It's all Rydberg atomic units.
It's on
Instances, it's like forces or maybe
Rydberg per word. Yes.
So you need to unit transform to pass into the
yes.
Yes. If you with ASE, you always use electron volt on Strom. Okay. Yeah. If we want to more control about this driver, we can use this iterative way. And this code, before they are the same, we import the driver, build communicator, and the only difference that we give an iterative to true, and that we can run iteratively. And we also put a log file equal to true, means that we want to get the output when we want to look at it. So first time I just get output because just initialization, so I didn't print here. But when I run downlies and I print output, so this is output when I do downlies, it will tell me about what's the threshold, some information here, and then I want to do the density mixing. When to do density mixing, he always calculates the NG, so that will have some output about NG. And then we can just run again. We repeat downlines and mixing, and we will see that iteration 2, total ng, and we can continue to write with 3, 4, 5, and always going. So because we don't want to do that, we just write a loop outside and check convergency, make it go, and we will see that the output will be the same as before we show the normal way. Still 27 steps to converge, error is the same, ng false, stress, everything is the same. So that's the way we can iterate to control it, and yeah, you can just play with it. And this is just a very simple example.
How do you add constraints? Like, you use ASE constraints?
Yeah, that's a ASE, but this is just a QEpy, we how to use it. Yeah. Okay, you see that now we didn't mention about any input file, and that's one thing that when we use a Python, we want to everything in the hand. So that's why we have another function can do it. We call a QEinput class that we can read the file and to update all the keywords. So the way we do it, the QEpy input have two styles. The first one is we call a name list, which start with this and symbol. You put all the keywords. Another way they call a card, which card that is just a name after name. They have several lines. So when we do it, we follow the same rules that for the name list, we just start with this and symbol and we put all the dictionary keywords here. But for the card, we put as a list. You just put each line on this list. And no matter how many lines you have, you just put here how many items in this list. For example, that if you have 2 atomic, you just put aluminum, one item, another is some other items. You just keep going to put it. Especially when you have item positions, you will have many lines.
And and if you have run Quantum Espresso before, this is very familiar because it follows the same structure of a Quantum Espresso.
Yeah. Yeah, the only thing to care for, because when we read the input file, if that value is a string, you have to use a double quotation mark to what it is, because otherwise we don't know it's a string. It will be maybe writing in a weird way. So that's the only difference. If you actually, that's the way when we define the string, we need a different quotation mark to make it. So that's why you will see SF, this prefix, which is string. That's a weird in the QE input file. So that's why we still follow it. We didn't change it. Document input and PWS. So for example, when we do this, they always use this quotation mark to close it. So that's why we have to output this one also. Otherwise, we will Python always remove this one. So if you don't put 2 quotation, it will just print SF without this one. So that's one thing you need to care for. And yeah, because I prepare this one also can run the different folder, or you run on Colab. So that's why I also have one line to download another file we call pseudo potential. So if you run the code, we also need a file called pseudo potential file. If you don't have this file, you can use this line to download. And maybe you also see why we have 2-1 is where QA options, another options. So this is I show example of how we update. Because for this name list also weird, because you have to define follow these orders. You cannot switch. I put the cars in front, name list later, you couldn't. So you have to follow the same rules. So that's why when we want to update some keywords, we can use these QEinput update options to update. So that's why we'll make sure the output will be correct, no problem. So here I put some basic options, and next I put some electrons mixing beta. Why I put here, I just show example that if I mix them, what's gonna happen? If you just write this way, it's not gonna work. Because normally if you define the input file like this, it will crash. But if you do these update options, it will correct the order. And we have these cell parameters. And maybe you see that we have key points in both. One is key points gamma, another one key points automatic. So this is also a way that when we update, so even you give a different key points definition, but when you update, we always use the latest one. So that's we can correct. So even you give a different way key points, you don't need to correct that. You just give what's on the real definition of the pw.x. So let's run it. And so when we do this update and we can print, you will see that in the beginning we put the gamma. Now we have these new key points, follow the correct order. And if you're wondering that, oh, you want to do some high-throughput calculation, you don't want to run the QEpy, you just want to prepare a bunch of input file. You also can use this function, just write the input file and update some keywords. So this is a way that you can use it. So I just read the input file, and we can see that what's the input file it looks like. So this is just the PWSF input file we will write on this style, which will be works. You can write input file and give to the driver as before, or you can give a Q options. So just a dictionary. And you can just give what we defined on the dictionary, and you give it. Is that initialization, and we run the electrons. Here, why I put electrons, I just want to people aware that careful about this, because our ISAC only works on normal exchange correlation. What do we mean normal exchange correlation? Means that when we do the hybrid functional, we are not working well. So if you just want to run that, you can call original function, which call electrons, which will be works for all the cases. Will be exact same as point expresso. But our modification only works for the normal exchange correlation, including non-analytical exchange correlation.
But not hybrid.
Not hybrid. Yeah, not hybrid.
Just everything except hybrid.
Yeah, everything except hybrid. So that's why if you don't know where to use it, just in case you can use the electrons. That will be exactly the same as normal pw.x. Okay, and why I stop? Because I want to show another example. If you're familiar with ASE, you want to build some items with a different thing that, or you want to update the input file. For example, that you prepare a PWSF input file and everything is the same. I just want to do a high-throughput calculation. I only need to update the positions, structures like cell parameters, atomic positions. You can use this module. This function, you build a bunch of ASE items. For example, that I build ASE items which have 4 items with FCC cell, and I can use these update items, only update the item positions, keep others keywords. So I update, I print, and you will see that before we only have 1 items, but now we have 4 items in these options. And we can run initialization, and we run electrons. Why I divide 4? Because before we only have 1 items, so we get 39. But now we have 4 items. We just want to double check. We divide by 4, which we give the same energy because they are the same structure, only in different definition. That's it. So this is an input file. I hope it works for helpful for some people. If you want to do some high-throughput calculation, you can just use this one to prepare input file and to make it easier to run some calculation. Yeah. I think I have another 2 examples in SF folder. Okay, the first thing that and now we have these QE options. I said that we can get the density during the SF. So here is just a simple example that we get the density and plot and to see how the density changed during the iteration. And we just write each step, we just plot the first 10 points and we see how density changed during the SF, and we can see that finally density, they are the same lines. So that's why they converge. So it's just a simple example. I didn't go too detailed about how we set density, how we set potential, how do the embedding potential, because when we give it potential, if you give the external potential, it's fine because QE, they do not have external potential, you can direct add. But if you want to modify some potential, but I want to define a different extreme correlation, or I want to give a different local pseudo potential, how I do it. So that's you need to give another keywords. So we can leave it to the next tutorial because we don't want to talk too much. And we also have some real-time TDDFT I also did not show today, but we do have some a ground state example here. Yeah, I also want to show, because we have another code, DFT-Pi, which is a density functional code. We can calculate the potential, everything that. So here is example that how we get density to the DFT-Pi field. And based on the DFT-Pi, we can calculate kinetic energy, external potential. We can do anything like when we do embedding, that's what we did. So when we run the same thing, and we just need to get the density and transfer the density to DFT-Pi field. And this DFT-Pi field will be, can do the FFT integral, all the jobs. And you also can write as a file to visualize with a different code and to look at the density potential. So this is an interface. So you to use it. Yeah, that's for SF. I can go to, so I also, maybe we can do some testing here. So when I say testing, because for the plane wave function calculation, most time we test the two parameters. First thing is that cutoff, that because you is define how many plane waves you use. Another one is key points, especially when you use metal, you have to use a very big key points. So that's why most time we have to test. So you can use normal way to test that. And here we give an example that with QEpy how you do it. Same as before, we prepare a Q options or you prepare your file, nothing changed. Same as QE. The only difference that we have these QE options already. So you only need to update key points because that's the value we need to change when we do the test of key points. And you run the driver, stop, save the energy, and run again. And finally print the key point, the energy versus energy difference versus the key points. And you will get this conversion line. You can select which key points, how large is good for your calculation. So this is just a simple test. I can just write. Because yeah, you see the largest we are using 10, and so it's a big key points, but still not slow here. And we can see this plot very quickly. And another test is a test about cutoff, and in the quantum expressor, we call it cutoff for the wave function, or another one is cutoff for the density. But if you don't set it, it's just 4 times of this cutoff of wave function. Actually, this time we need a different density, but just for simple, we just test 1 for the wave function. And we do the same thing that we give a list about which key points, which cutoff we want to test, and we give to the key options. And you will see that exactly the same as what we test on the key points, because we only need to update the input options. And we will plot this one, and we also can write. And we just click, right, and go to a few points because we use a very big key points, make it very slow. But this is a real test. If you run a calculation, you will get some point like this. You don't have to run the script. You get to read the file, get the density, get the ND, plot the figure. Now you can direct get it, or you can just look at the value. And last thing about some parameters, not most time we didn't test, but actually we are still working on that. I want to make it easier for people to use, but this is just not final version, but still works. Yeah, it works. For example, if we want to test degauss, so this is when we do the band calculation, we have smearing. You have to give let's see, the width of this smearing. So we have called a keyword called degauss. So these keywords you also can use original way. You just run it, or you don't restart it. You just you just update, because the density we already convert. So you don't need to from scratch to run. You just can use the convert density and directly test the variable, because the density already converts. If you directly calculate the engine, make it much faster. It won't take time. But if you test as original idea, and every step, if you stop and read from the random wave function and rerun the calculation, so it will take longer. So for example, in this case, if I test file point, take 9 seconds, but if I derive from density, I just need 2 seconds, which will give me exactly the same engine. So this tells us that if we want to test some parameters, which will something that we can directly modify during the runtime, so we can directly use this way. But what we do now, because I know it's just here on the key list, I use this side. We want to do something like a driver updates parameters, something that make it people easy to update some parameters and make it easy to use to test.
If you code with the quantum espresso, you will recognize K-list as one of the modules.
Yeah. So yeah, this just give an idea about why we use this Python way to do it, because in some tests it will be save time save some time in real calculation. For example, for this test, later I will show you on the US also save some time, because we don't need to from random wave function to calculate run SF, because we already have to converge the density. We can directly from the last step density run the next step calculation, and they are on the memory. We don't need to read save. That also will be waste a lot of time, and this one will be much faster. I would like to show some actually a simple real calculation. Like sometimes we want to run a US calculation, right? Equation state. We want to get this line, actually just this line. So how are we going to do it? We just change the volume and run the calculation and change a different volume, get the NG, and use another code to plot the figure, get the value. But ASE, that's why I prefer ASE. ASE already have a function can do it, or equational state, and can help you to get all the variable, all the values and plot the figures. And when we write, because we already have this QEpy calculator, we just give the Q options the same as before, and we have this use ASE to build a aluminum FCC structure. First time we get the cell, because we only need to just scale the cell parameters. So what we did here, we just from the 0.9 to 1.1 of the scale of the cell, and we set the cell, we get volume, get NG, that's all we need. And finally we will plot like this. So this is an example that we use ASE to run some calculation. Later we also will show some like a band structure, DOS, and some other features with Python interface. Yeah, that's it. Thanks.